Okay, so moment of inertia for a disk. All right, we've already done it. Moment of inertia, I. All right, and we want to look at I for a disk. Okay, so let's draw a disk. Okay, and it has some axis. All right, and it also has, I'm not doing this justice. It's got a width, right? It's got some, width to it. And okay, that's better. And let's see, let's make this distance here h. All right, and it's going to spin around this axis, so that's where omega is going to happen. Okay, that's one axis, but then right through the middle of this thing we could have another axis. Okay, so let's call, well, that's not very straight, is it? I mean, anybody could see that. Let's do it straight. Okay, and this one, if you make it thicker, then it's harder to tell that it's not straight. All right, so let's call this axis 1, and we'll call this one axis 2. Okay, fine. Our disk has a radius r, and let's give ourselves some numbers. You guys like numbers, so let's do it. 0.5 meters. So it's a full meter across. Okay, that's a big disk. It's got a lot of mass. All right, we're gonna do the mass of the disk. That mass, is 42 kilograms. And we can put H on there. We'll talk about that a little bit. And we're going to just say that it's 0.1 meters, so 10 centimeters. All right. So when we want to rotate about axis 1, we're going to get a certain I. Okay, now there's a diagram. I think you guys have already seen. I think you've already seen it. I'm gonna cut, maybe. I might edit. Who knows? We'll see if I do or not. What chapter are we on again? Rotational motion, chapter 10. Moments of inertia, rotational motion. Doom, 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 there it is. Making connections. Figure 10.11. Okay? Because, listen, it's not hard. We can do it. I do it from my other class, and I could do it for you guys. If you really wanted to, we can go through and derive and I could put on the test, how do you derive a certain thing? And you're going to be like, what? No, gosh, I don't want to do that. So we're not going to do that. We're going to go to this figure 10.11. Okay, so figure 10.11 in the book. You're going to go there and you're going to look for the second thing down from the left on the first column, the second one down. Okay, it looks like a rod, but it's just you could cut the rod. All right, so we could lengthen this rod and make H really long if we want to. Okay, we could make H longer than the radius, but let's not. Let's keep H short, and we're going to go to that figure every single time. Now, when it comes to the test, I'm going to give you what you need. So I don't want you to go writing in the test what these things are. I want you to know how to use them. I don't want you to have to memorize it. Okay, so what are we going to do? For axis 1, we're going to say I disk is equal to, and then we just write mass of the disk, and we're going to multiply that by the radius of the disk squared, and then we're going to divide that by 2. Okay, and it's very easy. All right, so mass disk radius 2. So this is actually, when I did my wheel earlier, we were talking about the wheel for it used to be Bob Barker. Who is it now? Drew Carey on the Price is Right. So let's go back up to the Price is Right wheel. And what did I say? I said that we were dealing with mr squared, right? But that's wrong. That is not true. Our solid disk, this solid disk, is 1/2 mr squared, okay? So that is the correct moment of inertia for a disk. So when we go through and find different moments of inertia, we do it just basically you go and you look it up. Okay, I'm not going to tell you how to look it up. When we did this one, when we did this one right here, we essentially considered each of the barbells a center of mass, and they were both rotating about some point, our pivot point, like this, okay? So, with some omega, all right? But we were just basically considering that center of mass. We're not worried about the stuff between here and here, all the stuff that could be here in a disk, there's stuff there, okay? And all that stuff, you gotta account for all of it. So we don't have to, in the barbell situation, we don't have to account for it. So it ends up being mr squared for each, okay? On a disk, it's definitely not mr squared. Should we talk about it? Should we talk about why? Let's talk about why. So we've got our disk. I'm going to erase this in a second, but I want to talk about it. So let's look at the disk from the top down, and we're going to spin it around this way. Okay. So if I were to take just a little section, just some little mass, right? I take some little mass, and every one of those little masses, if I were to add it all up, I'd have a whole bunch of little masses that if I summed all of them from I equals 1 all the way up to n, we've got n of them, okay? So if we put n of these things all together, we would have all the mass, right? And each one of those has an r. So some of the r's are big, some of them are small, and it turns out this would be our total mass of the disk. It turns out if we add up all of those things, we're not dealing with r all the way out here, okay? We're not dealing with that. We're dealing with an r that is less than that for most of the masses. Most of the masses are in closer, so our r is closer. So in order for us to do it right, we go through and we count, okay? And we count all the stuff together. So I disk would equal the sum of all of those little masses times all of their little radii squared. And we would do it for each one. So I could call this Ri. And we could do it from each one to all the way, I'm sorry. Jeez. Okay. All the way up to n. When we do that, okay, we're going to add them all up. When we do it, it turns out, and like I said, I don't want you guys to have to go through and figure out how to do this. So you're just going to take it for granted that the net R that we end up with in the end, if we were to divide the whole mass by 2 and square the whole radius and multiply those two things together, we would get the disk. Okay? So that's how it works. And when I was doing the barbells, we had one mass on one end and one mass on the other. And we were just spinning them around this one axis in the middle. Okay? So I was using it. Basically, I had 2 of these. All right? N equals 2. And the L was the same for both, so it made everything easy. But that's not how the real world is, right? The real world has extended bodies. So extended bodies require a little bit more work to figure those things out. So we're not going to worry about that work. We're not going to say, oh, this is easy to do because it's labor intensive, right? There's our homework problems and all kinds of other stuff associated with doing it. So we're just going to figure out those things. We're going to refer heavily on figure 10.11. Okay. Let's do axis 2. And I wrote, listen, I've shoveled too much snow lately. And that's my excuse for all my mistakes. All right. So we're doing axis 2. Now let's look at it because let's look at it from the top down. So imagine this is maybe it's a quarter. Okay, you're looking at a quarter purely from the side, and you're going to have your axis right in the middle. Okay? Well, this is the same as if you look in that column, it's the one just down from the one we were just talking about. So third down on the left. Okay? And it's a thin rod. We're calling it a thin rod. All right. And our length, wait, no. Is that the one I want? Is that the one I want? The one I really want is the one on the right. Second down on the right. Do I want that one? Are we gonna keep it thin? How thin is it? How are we doing this? We're rotating that way. Okay, it's not really thin rod. It's not really a thin rod. I'm not gonna do it. We're gonna do the axis 2. Okay, so look at second one down on the right. So let's just write out what that is. So it would be I disc is equal to 1/4 the mass of the rod or disc, and first the radius squared. Okay, so we're to 1/4 mass of the disc times radius squared, but we also have to add in 1/12. And here's where we have our mass of the disc, and instead of the length of the disc, we're using our height. Okay, so it's the height squared. Okay, so now we're spinning this thing like that. And there's about the center, about this axis. Okay, that's our pivot point. Yeah, now let's say we make it a thin rod. How do we make it a thin rod? Well, we reduce R to the point where L is much greater than R, okay? In what I've drawn is this. H is not greater than R. I'm going to change it. I'm using L and H equally. Let's change it to, here's H. So now let's make H a lot longer, okay, so than R. So we would be making it like this. And that is the third one down on the left. And our H goes all the way out to here. And equally on both sides. So it's balanced. This would be axis 2, but with a thin rod. All right, axis 2 with a thin rod. That makes things a lot easier because basically this term dominates. This R is so much smaller than the H, and so the R goes away essentially, and we end up with I disc equal to 1/12 the mass of the disc times H squared, where H is really the length of our rod, right? So we've got 1 here, and that's pretty much always the case, this one. Okay, it doesn't matter which scenario we're dealing with, whether R is bigger than L or not. And you can see that because the axis goes right down the middle, okay, of the cylinder. However, when you're not putting your axis right down the center axis of the cylinder, then you have to deal with the length of the rod as well, okay? So we've got 3 that we've just covered. And I hope it's clear why we chose them the way, or it's clear how I explained it, hopefully. Let's put some numbers to these guys. And here's where I would normally have you guys hooking me up with some number calculations. I disk. And we're gonna do axis number 1. I disk. So we're gonna do 1/2 mass of disk times the radius squared. So we've got our 0.5. So 42 divided by 2. That's 42 divided by 2 is 21. So we're gonna multiply. I'm just gonna put 21 here. Then I'm gonna square 0.5. Okay. And times 0.5 squared. So you can do the math if you want to. I'm going to do it. And we end up with I equal to 5.25 kilogram meters squared. Okay, and that's our I of the disk. All right, our moment of inertia for the disk. Let's do axis 2. So it's still the moment of inertia for the disk, but what are we doing? We've changed the axis of rotation. The axis of rotation matters, okay? So now we're going to put in 1/4 mr squared. Well, 1/4 mr squared, that's going to equal just half of what we came up with just there. So 5.25, enter 2 divide, is 2.625. Okay, so I'm going to write 2.625 right there. And we're going to be adding that to our 112 mass of the disk, which is 42 times 0.1 squared. So what is that going to be? 42 enter 12 divide 0.1. We're going to square it, multiply it. 0.035. 0.035. And all of this is kilogram meters squared, and it's going to give us an I disk equal to 2.625 plus 2.66 kilogram meters squared. So let's go back. Notice how our moment of inertia is less. We calculated, we did the math, we did all the stuff. Our moment of inertia for this thing around this axis is less than the moment of inertia around this axis. So it may not be intuitive, but maybe it is. I don't know. There's a lot of ways to think about it. Most of the item lies in this region. Most of it lies here. The moment of inertia isn't very far away. So that's a lot of it. And gradually it gets smaller and smaller and smaller till you actually get out to that full radius. So the moment of inertia really declines. There's less and less and less as you get further and further away. So the moment of inertia is going to be quite small comparatively to having a lot of, in the other way, We have a lot. Let me get rid of these things. In the other way, a lot of our mass is further away, right? Most of our mass is in the crust of the pizza out here, right? And all that is really far away. So you should expect that our moment of inertia in this situation around axis 1 is going to be larger. And when we go back through and we do it, it's roughly 2 times, right? We are roughly 2 times larger around axis 1 versus axis 2. So, is it 2 times? I'm going to multiply by 2 and see what we get. 5.32. Okay, so this is slightly more than 1/2 of it. Slightly. Now, what if we make h really long? Okay, this is our last thing. So I'm just gonna write real quick. So our mass of the disk is equal to 42 kilograms. We don't care about the radius anymore, but we're gonna make our length really long. Let's make the length super long. So don't forget, it's still like this meter diameter thing, okay? So maybe it's made out of styrofoam instead of copper or something, but we're making it really long, so let's make it 5 meters long. Okay? No, better yet, let's change the radius. Let's drop the radius down. We'll still make it 5 meters long, but we're going to drop the radius down to 5 centimeters. Yeah. So we've got this long... That was good. That was pretty nice. We've got this long... Boy, it's almost better to see me do this on the chalkboard, right? Okay. L equals 5 meters. Our radius is really small. In fact, it's so small comparatively, we don't even consider it. It's not a part of our thing. And we're going to put our axis right down the center of this deal. Okay? Now, there's quite a bit of mass far away, right? There's quite a bit. So, all we have to do is go to our handy table 10.11, 10.12. I don't think they've changed it. I think it's still 10.11, but you'll know it when you see it. And we go to this one and we say, what is the I for this thing? And in this case, we're really talking about a thin rod. So I'm going to say it's I have the moment of inertia for the rod, and that's the mass of the rod times 1/12. I'm always used to writing 1/2, so writing 1/12 isn't as easy. And then length squared. All right, well, 5 squared is 25. And I've got 112 out front. I've got 42 here and 25 here. And I know that it's kilograms meters squared. That's my units. So good. What do we end up with? I don't know. Maybe you guys like to stop and plug these things in, but you can't help me. So I'm going to do 12, 1 over that, times 42. times 25, 87.5. Okay, and this kind of makes sense. How is it? How easy? Have you guys seen 5 meter long anything? 5 meters is a long way. 5 meters is 3 times 5 is 15 feet, roughly. All right, and I wrote inches, but I meant feet. It's 15 feet. So 15 feet. Take a long piece of rebar, 42 kilograms. 42 kilograms is heavy. And try and spin it around the middle. It's not easy. So doable. You can do it. A person could do it. It's just that's why it's so incredibly much more than this one here. Just spinning around an axis. Like, what would it be? Like a manhole cover, right? The other one was like a manhole cover. This one is like a long piece of rebar. So let's get to a problem. I want to do problem-solving strategies. In fact, what I'm going to do is I'm going to just note the. I'm going to put some markers in here for problem-solving strategies. I want to hit Monday before we start our lab. It should help. But before we do that, I want to do the boy in the bowl. I have all these little stories. So the boy in the bowl. All right. I don't know if you've ever done this, but you know, you're out in the prairie and there's maybe a bull. Ranchers, they keep their bull separate from the other cows, especially during the mating season. So we've got some bull out there. So we've got a big nose, and oh my god, here's his body, and there's his stick legs. Okay, so there's the bull, and he's scary. Okay, well, there's a gate. All right, there's a gate. We're going to zoom in on the gate here in a second, but there's this gate. And it's big enough for the bull to get through. All right, it's a big gate. So the boy has to go and close the gate. All right, before the bull gets out. I don't know, maybe his uncle said, if you don't keep that bull in there, you're in trouble. And he left the gate open. I don't know, maybe he was carrying water out of somewhere into someplace else or something, and he left the gate. So here's the thing. If he doesn't get the gate closed, the bull will get there because the bull wants out, right? The bull's trying to get to the cows. So the boy has 3 seconds. All right, not a lot of time. So let's just say 3 equals t. And let's analyze this gate situation. So yeah. I'm pretty sure we're using 1/3 ml squared for the gate. Yeah, it's an eye of a rod. However, it's not really a rod. So let me draw the picture. Here's our fence. We've got some gate. And the gate is open. So here's the gate. And the boy has to get this closed. Okay, and so the boy is going to do force of boy here on the edge of the gate, okay, because he's using his mechanical advantage as much as possible. Where's the pivot point? The pivot point is here. What does that mean? That means our axis of rotation is there, okay, and then we're going to swing this thing closed like that. All right, so that's our goal, all right, and we have to do it, right? We've got to get that gate closed or we're in trouble, right? Maybe our the uncle might be super mad. I don't know what kind of punishments they do out on ranches anymore, but it used to be not great. So let's know what the boy can push. So the force of the boy is equal to 100 newtons, all right? He's not super huge. And is he pressing perpendicular to the gate? Yes, he is. So he is pressing perpendicular to the lever arm. So our theta is equal to 90 degrees. Sine of theta is equal to 1. Okay? Just keeping it easy. What's the distance that he's pressing? That's this distance here that he's pressing away. This distance. Okay? That's 2.8 meters. All right? 2.8 meters. So the radius or length, we're going to consider it a length. Yeah, we're going to consider it a length of the gate is equal to 2.8 meters. All right. Okay. We're going to figure out some things. We need to know some other stuff before I start asking questions. What else do we need to know? You can pause it if you want and figure out what you need to know. But we need to know the mass of the gate. So mass of the gate, that is 153 kilograms. We've already mentioned that the radius of the gate where the boy is going to press, or L, however you want to look at it, is 2.8 meters. So we've already done that. What is the height of the gate? What is this height here? Because the gate is the same height as the fence. And the height is equal to 1.5 meters. Probably taller than the boy. So we know T, that's as much time as he has, and the other things. That's all we got. So let's put in the eye of the gate. It's the same as the eye of a rod. So it's 1/3 mass of the gate times the length of the gate squared. And I'm going to now call it I gate. All right. So we have a few questions. A, what is the moment of inertia of the gate? Well, we kind of just laid that out. So let's do it. I gate is equal to 1/3 of M, 51 pounds, or kilograms, 51 times L squared. So I got to square 51 times 2.8 squared. That's my I of the gate. So let me come over here to my thing and do my little calculations, and I end up with 400 kilogram meters squared, and that's equal to my I of the gate. Okay, what's my next question? Next question. B. What is the angular acceleration of the gate? What is the alpha? All right. So, couple of things here. We've already said earlier that the torque is equal to I alpha, but we also know that the torque is equal to the radius times the force, especially when it's perpendicular, because we don't have the sine. The sine of theta is 90, so the sine is 1. So we have this equation, and we kind of know all those things. So we can figure out alpha is equal to our radius, or length, times the force divided by I. So we've got 2.8 times 100 is 280. And we're going to divide by 400. And we're going to be left with radian per second squared. And that happens to equal 0.7 radians per second squared. So that's our alpha. All right, our third and final thing that we need to know. The gate has a theta that it's open. Okay, so that theta that it's open is equal to 50 degrees. All right, different theta. We're not talking about the theta between the force and the radius. That's not a theta anymore. We already decided we don't need to worry about that one. I'm talking about how much does he have to close the gate. 50 degrees, okay? So if he has to close the gate 50 degrees, how long does it take? And hopefully it takes less than 3 seconds. Our t that we find needs to be less than 3 seconds, or we're in trouble, right? Either the bull's going to get us or our uncle's going to get us. One way or the other, it's not, or both. We've got double jeopardy. So we want to make sure we get the gate closed. And okay, so how long is it going to take? Let's find out. We have theta equals omega naught, which, think about what omega naught is, times time, 1/2 alpha t squared. Omega naught, of course, is the initial movement of the gate, which is nothing, right? It's nothing. So omega naught equals 0. So that leaves us with theta is equal to 1/2 alpha t squared. So not terrible. We can figure out t squared is equal to 2 over alpha. Let's rewrite that. 2 theta over alpha. And we can take the square root of all of that. So that gives us a t is equal to 2 theta over alpha square root. So 100 divided by 0.7. Oh no. Uh-oh. What do we have here? Let's get rid of my oh no. Everyone should be saying, oh no, this is no good. I have theta in degrees, but I've got alpha in radians per second squared. All right. We got to do something about that. What is 50 degrees in radians? We have to solve that. So 50 degrees in radians. 2 pi radians equals 360 degrees. This is where I start out every time. You could start out with pi radians equals 180 degrees. That's fine. But then what we need to do is multiply 50 degrees by something. So let's do pi radians, and let's do 180 degrees. Blah, 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 blah. 180 degrees. So if you divide one of these by the other, you get 1. So I'm going to multiply my 50 degrees by pi and divide by 180 degrees. And that's like multiplying by 1. And I'm going to end up canceling out my degrees, and I'll end up with radians. So 50 divided by 180 is going to be 0.87 radians. Ah, that's so much better. So now I can say, I can come over and say that t is equal to the square root. And this is still theta, by the way. It's still theta, by the way. So square root, okay. 2 times 0.87 divided by alpha 0.7, and I'm going to square root that thing, and that's going to give me some t is equal to 1.58 seconds. Awesome. I don't know if you guys know what 1.4 seconds seems like, but you get that closed and then the bull will stop, because he doesn't want to hit the gate. And in that last second, he stops, and the boy's like, whew. All right. So really the bull never had a chance, but, it was kind of close. All right, guys. I'm going to stop there.